Welcome back, Chemistry 230, Organic Chemistry 1. Now we are with the second half of chapter 7. Remember that this chapter has two sections, right? So we have first the substitution reaction, which was covered before with this reaction on 7A. And then now it's going to be touching base on elimination reaction. These two reactions, they share many things in common. Okay? So remember for nucleophilic substitution, we had SN1 and SN2. Now we will have E1 and E2 reaction. The rules follow about the same. Of course, we have different products. Right here, what we get is a substituted product, a substituted substrate. In elimination reaction, we lose the substrate and we create an alkene. It's a new functional group that we will learn how to make it. The purpose of this chapter 7A is to make the alkene that is going to serve as a foundation, as a starting material for chapter 8. Chapter 8 will be addition to alkenes. So we will learn what to do with the alkenes that we make on this particular chapter 7B, right? So remember that right now we are on 7B, right? So just to give you an overview of what we are going to be doing, so I'm just going to turn on my camera right now. We will basically do two reactions, and then all the mechanism details and stereochemistry associated with E2 reaction. We'll start with E2 reaction by molecular elimination. The 2 subindex, it means exactly the same thing it meant for SN2 reactions bimolecular. That means that the reaction depends on 2 species, the substrate and the base. In this case, we're talking about the base. That's the main difference between elimination and substitution. And then we went over that on chapter 6, but just in case we'll repeat. A base is a substance that is electron rich, but targets hydrogens. Nucleophile is also electron-rich species, but it targets carbon. In our case, it targets carbon. It can target something else. Let's say you're doing chemistry of phosphorus, chemistry of, let's say, of silicon. Of course, your target then would be the silicon and the phosphorus. But in our case, our main target for elimination reaction will be carbon. Okay. So if I see that, for example, like a compound, let's say an ion OH minus, right, is attacking here, acetic acid, let's say, attacks to steal, right? To steal this hydrogen, right? So here it is, OH is acting as a base. Okay. If OH minus attacks COO, here is attacking a carbon. So if it's attacking a carbon, here is behaving as a nucleophile. Okay. Same species, same charge, same everything. So the only difference is that in one attacks a carbon and another one attacks a hydrogen. So for this particular set of reactions that we're going to study today, we're going to see what are the properties or what are the characteristics of working as a base. Of course, we are not going to be doing an acid-base reaction like in this case, but we will be attacking a substrate. Here now, this one is going to change, and now we will have a substrate. Substrate, for example, a chloride, right? That has a leaving group. So it will attack it. Now, is it going to attack this carbon? No, we will see the details. It's not going to attack it specifically, right? This particular position, but the idea of the attacking a hydrogen is there. So we are definitely going to be attacking a hydrogen. It's only that that hydrogen is not going to be, sorry, the hydrogen is what makes it a base, right? So that's the main idea for elimination reaction, is using bases. We're not going to be using nucleophiles. And it will be basically the same characteristics that what we saw for SN1 and SN2, right? Remember that in SN1 reaction was 2 steps. E1 is also 2 steps. SN2 was 1 step concerted. E2 is also concerted 1-step reaction. Yep? So they share many things in common. So at least to learn from scratch for this particular reaction is not going to be the case. We will use a lot put these 2 reactions in parallel, right? All right. So here, substitution, they use, as we mentioned, they use the same substrate, right? So we will use here the substrate, which is an alkyl halide. Remember, this alkyl halide can be replaced by something else, right? So something else like tosylate, which are also good leaving groups, or a protonated OH, OH2 plus, right? This OH2 plus is also a good leaving group. That one can also be eliminated. and tosylate, OTS, right? OTS is also another group, can be eliminated. Remember that both of them can be created from alcohol. All what we're doing is just brushing up all things that we saw on chapter 7A. So that one was the purpose of substitution, was the purpose of chapter 7A. Now we're in elimination. We're going to be using a base. Base is really the key term here. And as you can see, we're producing an alkene. Okay, so double bond is being produced in this particular compound. Don't worry about the other species that are produced. Those are side products, byproducts of the reaction. So they are really not important. So the most important part is that we're producing an alkene. Okay, so alkyl halides can undergo an elimination reaction when reacted with a base. Okay, so now that reacting with a base is really depending on the scenario. And then that's why we are dividing. I mean, we are lucky that in this course, we're separating 7A from 7B. Because normally you guys will have to assess. You guys normally will have to look at the molecule and say, oh, in this case, I think OH behaves more as a nucleophile, or it behaves more as a base, right? In here, no. Here, the question will be very clear. It will tell you, please draw the substitution product or draw the elimination product, right? So by knowing that you are doing elimination product, right? So definitely you know that you're doing an E2 or E1 reaction, right? So you don't really have to debate between four different reactions. Okay? So it is a little bit simplified in this way. So if we divide the chapter in 7A and 7B. Okay, so what do nucleophiles and bases have in common? That they are both electron-rich species. They can be neutral, they can be charged, and they are able to donate those electrons. That's very important. For example, Br minus, can Br minus be a base? No. I mean, can I use it as a base in a mechanism? Yes, but use it as a base in a reaction like what you guys see right here is very unlikely. There are some species that are not good bases, even though they have electrons and they have a charge. Okay, so we will see what are the available bases that we will have for SM1, for E1 and E2. And based on that, I mean, you guys will judge about the criteria, right? What is necessary to be a good base. Okay, so in this particular case, we have sodium hydroxide, right? Which is a chemical that we know. We study it on chapter 7A. Here, if you evaluate the substrate, we have a secondary substrate. If you don't know, I mean, or you are not sure about what is a secondary substrate, please go back to chapter 7A. We go in detail about selecting or labeling substrate. Because this one is a secondary substrate. Secondary substrates, they can do either SM1 or SM2. Okay, so if you have an OH, that's a strong nucleophile. That means that this reaction is going to be SM2 reaction. That's what I have here, substitution. But this reaction, as we mentioned, is also going to compete. Why? Because OH is not only a good nucleophile, OH is also a strong base. Okay, so if it's a strong base, it will also do E2 reaction. How do I know it's a strong base? Well, I will give you a list of bases that are strong and a list of bases that are weak, right? So in this case, I'm telling you that it is a strong base. Therefore, if it's a strong base, it will do E2 reaction. That is your elimination. And as you can see here, it says elimination product, major product. So that means that in this particular reaction, the elimination is favored, right? It's more favorable than the substitution. Why, right? Because OH is a better base than nucleophile. If OH is a better base than nucleophile, then definitely it will do a better E2 reaction. Now, Professor Navarro, how do I know? Do I have to memorize it? Is it that? Technically, yes, you will have to memorize what is. But to be honest, I mean, over the years, in my case, I've been doing OA and elimination substitution reactions that I see that what is the preference of each of the species. For example, I know OH is a better base. Cyanide, for example, Cn minus, we used it for substitution reactions. If you add cyanide, if you replace here sodium cyanide, it will be opposite. This one will be your major product substitution, and then elimination will be 0. Why? Because cyanide hates to be a base. It is a better nucleophile. Okay, so see, how do I know that, right? Is there any rule, anything? No, there is nothing. There is no rules behind it. It's just like some species, they prefer to be a better base. Some species prefer to be a better nucleophile. But on your advantage, as I'm telling you, this slide and also the previous slide, you guys don't have to deal with that distribution. You don't have to figure out if it's a better elimination or better substitution. All you guys have to do is you are going to be asked, write the elimination product, write the substitution product. So you know what you have to do for in our class, right? Right. So in the example above, which compound is the substrate? Oh, this is my substrate, definitely. Yeah, these questions, they are very straightforward, right? So let's continue. Something that's going to be very important. We also use this slide on chapter 7a. It's about the structure, right? So how to assign letters. In our case, we have alpha carbon, beta carbon. If you have a hydrogen here, that will also be alpha hydrogen, and here you will have beta hydrogens. There will be gamma hydrogens right here. For a substitution reaction, everything was involved in the alpha position. C alpha, hydrogen alpha, carbon alpha, those are the key points. Now, for elimination, we actually care about the beta hydrogens. Beta hydrogen here, and also this beta hydrogen right here. Okay, so both beta hydrogens are important for elimination reaction. Okay, so why is that? What's the difference? Because now remember, you guys are going to be making an alkene. So the alkene definitely has to be established between two carbons. One of the carbons is going to be the one that holds the leaving group, and then you have to get another carbon, which is going to be the adjacent, right? The vicinal carbon has to be the one to be an alkene. You cannot make an alkene with only one carbon. To make an alkene, you need two carbons. So it's going to be either on your right or on your left of the carbon that has the leaving group, right? So that's why it's going to be very important. They will play a very important role. The beta hydrogens. Beta hydrogen, for example, like here, right? So here you have hydrogen, another hydrogen. Let me clear this because it's a little bit. Okay, so once again, here I have hydrogen, hydrogen. Here we'll have also 3 hydrogens. So those are my 3. I have in total 5 beta hydrogens in this particular compound, right? If I have 5 beta hydrogens, that means that I have potentially 5 different elimination products. Now, am I going to be producing all 5? No, it will be definitely a major product, right? So that's going to come soon. It's like, but remember, are those hydrogens beta hydrogen? What about this alpha hydrogen? Something happens to this alpha hydrogen that is right here in circle? No, nothing happens. Why? Because that carbon is only losing the leaving group. That's all it does. There's nothing else that is going on with that alpha carbon. Nothing happens to the alpha hydrogen, right? Even in the most basic conditions, it will not occur anything to that alpha hydrogen. Do not touch it, right? Substitution occur at the alpha carbon. Yeah, of course, that one substitution, we already went over that. And then elimination occurs with involving the beta hydrogen. Why is it beta hydrogen? Because it needs to be an adjacent carbon. An adjacent carbon so you can form your alkene. Alkene means 2 carbons, right? 2 carbons are forming a pi bond. So definitely you need that interaction. I mean, that particular second atom. 3 types of alkyl halides. We will use this again: primary alkyl halide, secondary alkyl halide, or tertiary alkyl halide. This one is an alkyl halide, but I mean, you can also call it primary substrate, secondary substrate, and tertiary substrate. Because remember that we're using different type of leaving groups. We're not only using halides, you're also using tosylates, you're also using OH2+, right? Protonated OH. Okay, so let's start with the very first reaction. Ready? Okay, good. So you can just get some water, get a snack or something, but you guys are watching and listening to this video. So E2 reaction. What is important about E2 reaction? We need an alkyl halide. Once again, we are going to be talking about alkyl halide, but we really mean substrate, right? Substrate that has a good leaving group. So it's treated with a strong base. That is one of the requirements for the E2 reaction. It has to be a strong base. It cannot be a weak base. And now I'm going to make a pause to tell you what are the strong bases, right? So because that is, okay, so let's start by doing that. What is a strong base? Okay, so a strong bases. And I will put a parallel with the weak bases. Okay, weak bases are alcohols, any alcohol, ROH, and water. Those are the only weak bases we're going to be using. What is this ROH? That could be methanol, ethanol, propanol, isopropanol, right? Any neutral, I mean, really any alcohol. That's ethanol, that's a weak base. Methanol, that's another weak base. Propanol, like so. What is a strong base? The strong base is going to be the conjugate basis of these bases. So for example, I'm talking about methoxide, ethoxide, propoxide. Okay? So all the oxides, all the deprotonated alcohol, this one is called methoxide. It used to be here called methanol. Now here is called methoxide. This one is ethanol. Here is ethoxide. Okay? So you always use the conjugated bases for each of the alcohols. Okay? So of course you only need one, and of course OH, right? OH is the conjugate base of water. These guys are going to be strong bases. So one thing that I didn't mention, I think I should have started with this, is that remember that SN2 reaction, right? The reactivity trend used to tell us, oh, primary more reactive than secondary, tertiary, and SN1, we had that it was the opposite, tertiary, secondary, primary, right? Now in elimination reactions, E2 and E1, that is not trend like this. Okay, so in elimination reaction, it always follows tertiary, secondary, primary. Always, no matter what. Then how am I gonna judge? Right? So how do I know if it's an E1 or an E2 reaction? You will only do it based on the bases. Now don't look at the substrate, only look at the bases. Strong bases, E2, weak bases, E1. Oh, does it matter if it's a primary, secondary, tertiary substrate? No, doesn't matter. What matters is only the basis. Okay, it's different from substitution. Substitution, we had to apply this reactivity trend, right? And then if it's secondary, which they have in common, right? So then you will go to the strength of the nucleophile. That was substitution. But in elimination, no. In elimination, it's always the same trend. Okay, why is that, right? Because you always want to produce the most stable alkene, and in a second is coming that. What is a more stable alkene that's coming in a minute, right? Okay, so I will use a strong base for I need to reaction. It is going to undergo a beta elimination. Remember I was telling you the beta hydrogen, right? So here, for example, this one is going to be this one is the alpha position. Let me change the color of my ink because that red is not really that. Okay. So that's the alpha position. That's the beta hydrogen. So I call it beta elimination because I'm eliminating the beta hydrogen. Okay. So that's the term, the beta elimination. The whole thing is called E2, but they just label it as a beta elimination because it is the adjacent carbon, the one that loses the hydrogen. Okay. So the base will eliminate, and I can do that. Well, the mechanism is down here. So what really happens is, remember, it's a concerted reaction. The base attacks the hydrogen. This bond with the hydrogen comes down as a double bond, and the leaving group leaves. Okay. Now, is it happening like this? I mean, right now, this TS is really not appropriate. So it really looks better here at the bottom, right? So the base attacks, as you can see here, the base attacks the hydrogen, the beta hydrogen. This bond comes down as a double bond to form the new double bond, and then the leaving group leaves. Everything happens at the same time. It's one of the few reactions in which we have three arrows working at the same time. Okay? So base attacks, forms the double bond, and then the leaving group leaves. Okay. Now, do you notice something special with this transition state? This one will be the transition state. You see what is the relative position of the X and the H? They are opposite, right? So they're opposite. So why are they opposite? Do they have to be that way? Yes. Why? Because it's the same idea as an SN2 reaction. Just take a few seconds to remember about the SN2 reaction. And remember, why is SN2 under using a backside attack? So just think of that. 3 seconds. 3, 2. Why was it a backside attack for SN2? If you recall, in SN2 reaction, the nucleophile had to attack the substrate from the opposite side. Why? Because the nucleophile and the leaving group are electron rich. If they're electron rich, they cannot see each other. There will be like a high electron repulsion because they are rich in electrons. Same thing is going to happen here in E2 reaction. the base cannot see, this one is not allowed to see the leaving group. Why? Because they are both electron rich. They cannot, there will be a high electron repulsion. So the base has to attack a hydrogen that is totally opposite, diagonal, right? It's opposite to the leaving group. If not, the reaction is not going to occur. That's very important, very crucial for later on for some restrictions of the reaction. Okay, but that is what is needed. So what do I need to do? What if a hydrogen is not opposite? Then you will have to rotate it. That's why on chapter 4, we study conformers. Remember the Newman projections? That's exactly what we will bring back. We're going to do a Newman projection to determine how is the rotation of the molecule so I can do the correct elimination. Okay, so a strong base will react in a concerted mechanism. It's a one-step reaction called the E2 elimination. So the base attacks the hydrogen, the beta hydrogen, the bond comes down, and then the leaving group leaves, and then the beta hydrogen and the leaving group, they have to be the farthest apart in the molecule, talking about the from the steric, right? Steric point of view. The kinetics, here is basically explaining what means the number 2. We kind of like explained that already for SN1 and SN2, but that bimolecular, this number right here, number 2, means that the most difficult step of the reaction depends on 2 species. In my case, it's going to be my substrate and the base. That's why. Because if you see in this reaction, the reaction, this particular step depends on the presence of the base and also depends on the presence of the nucleophile. If it depends on 2 species, it has to be a bimolecular. What if it only depends on 1 species? Then it will be unimolecular. What if it depends on 3 species? Then it will be trimolecular. But in our case, we only have SN1 and SN2. It only depends on in this case, E2 only depends on the substrate and on the base. That's why it receives the label of E2. Okay. In what ways is E2 elimination similar to SN2 substitution? Oh, because it's also bimolecular, right? So in E2, you depend on the substrate and the base. In SN2 reaction, you depend on the substrate and on the nucleophile. Right? So that's the similarity between SN2 and E2. Differences. The attack, right? The attack. So you do the backside attack, on the same carbon. Here, no. Here you do a kind of like a backside attack, but you do it to the beta hydrogen. And you're attacking the hydrogen here. In SN2 reaction, you were attacking a carbon, right? That's another difference between elimination and substitution. Okay, so here is the substrate, right? So basically that's a parallel with SN2 reaction and E2, right? So in the case of a base, right? So it will have to attack from behind, right? It's in an SN2 reaction, but since it is a tertiary substrate, that SN2 reaction is not going to work as efficiently. So who is more accessible? If the carbon is not accessible for substitution, but the hydrogen is terminal. Remember, hydrogens are always well exposed. So the base is going to attack the beta hydrogen. Beta hydrogen is more accessible than the carbon. This carbon is too secluded. The hydrogen is more exposed. The beta hydrogen, right? We're talking about the beta position. The beta hydrogen is more exposed. Therefore, the hydroxide or the base, whichever is the case, I mean the strong base, you will have an easier time to extract the beta hydrogen and not attack the carbon of that has the leaving group. Okay, so when the substrate is theoretically hindered, E2 elimination will occur. Okay? So when there is much hindrance, that's why elimination prefers tertiary. Why? Because tertiary is more difficult to undergo substitution. Then comes secondary and then primary. Primary, they also do elimination, but you need a very strong base to do it. Right? All right. So these are few things about the substrate. Why is it preferring like that trend, tertiary, secondary, and primary? The tertiary is because it hinders the access to the carbon, making the beta hydrogen more accessible. Okay? Because of the steric strain, okay, so now we're talking about stability, right? So what is the alkene that we're forming? If we recall, there are 2 types of alkene. I mean, if they have twins, right? The transalkene and the cisalkene. We also have the E and Z. If we recall from chapter, also, I think we saw that on chapter 4. Right? We study E and Z alkene. Right? So they were having always the priority. but I mean, we use the priorities, right, for molar atomic numbers. But here, trans and cis is really referring to, here is the double bond. It's referring that the two bulky groups are opposite. So trans is always going to be more stable than cis, because if you think of the double bond right here, the two bulky groups, right, they are colliding. So this is steric strain in the cis bond. Okay, so that's only just to remember. Okay, so just to brush up a little bit on alkene stability, the trans alkenes are always going to be more stable than cis alkenes. And here we can see it in this graphical representation that the trans alkenes, they have less energy, right, than the cis alkenes. Cis alkenes, they contain more energy, they release more combustion heat. Now, what about the branching, right? So here we see different types of alkenes. This is what we call a monosubstituted. Monosubstituted means that the alkene only has one carbon branch. Okay? So one branch right here. Disubstituted is like that. This disubstituted is trans, but you can also have a disubstituted cis. Now, between the cis and the trans, which will be more stable? Of course, the trans is going to be more stable than the cis, right? So I would say that the cis disubstituted will be right here, somewhere around here. The trisubstituted is more stable, and the tetrasubstituted is the most stable, right, of the trend, right? So there is no, can I have pentasubstituted alkene? No, of course not, right? So alkene can only have 4 branches maximum. So you guys can have maximum tetrasubstituted, then tri, then di, and then monosubstituted. Why is that important to know this? Well, first is to understand, I mean, the stability of the alkenes, because it's a function that we will studying this chapter and chapter 8. And second is because it really depends on this stability. This stability will be the driving force for us to determine which of the product is going to be preferred, right? Because remember that whenever you guys do elimination, you always form an alkene with a beta hydrogen. But if you have 5 beta hydrogens, of course, one has to be a major product. Which of them is going to be a major product? The one that gives you the most stable alkene. That's why you need to know what is the most stable alkene, because that's the one that's going to be produced in the E2 and also in the E1 reaction. Okay, so more alkyl groups, more stable. And then here is hyperconjugation. You can read about hyperconjugation, what it is. But in general lines, I will explain that to you. Actually, I will. It's nothing better than a whiteboard. Okay, so you have an alkene, right? So you guys have substituents. Let's say I have a tetrasubstituted alkene. Okay, so if we recall, right? So the hybridization of this particular carbon is sp2. sp2 has 33% X character and 67% P character. It has some acidity, it's electronegative. So this carbon is electronegative. What does that mean, electronegative? That it will tend to absorb electron density. So an alkene that needs electron density, of course, is going to steal it from the neighbors. It's like a sponge. It will absorb all the electron density. So if you give to this, right, to this carbon or to this particular alkene substituents, then they will donate electron density. The alkene is more stable. But if you only have an alkene and you have only hydrogens and only one methyl, methyls, they don't donate anything. They're very cheap. They don't do anything. The methyl is the only one that donates. Oh, and then I'm putting an example of methyl, but it can really be ethyl, cyclopentyl, right? Any carbon chain, any carbon ring, any carbon source can be a branch, right? So here, this one only has one electron donator, right? Electron donor. So you have 2. Of course, it doesn't write when I need it. H, and I have 2 methyls, right? In this case, I have 2 donors. These hydrogens are quiet, they don't do anything. So this one will be more stable than this particular alkene, but this one will be more stable than both of them, right? Both of them will be less stable than that one because it has 4 donors. Of course, they don't. That is what we call hyperconjugation. Is that the carbon chains, they have some electron density, right? Because they have their field hybrid orbitals, sp3. So they will donate electron density towards electronegative center. Now, is hyperconjugation better than resonance? No, 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 no. Resonance is much better. It's a more stabilizing force than hyperconjugation. Hyperconjugation is only basically like it's a donation, but donation by orbital matching or orbital, like shading. Basically, the orbitals of the CH3, they are basically leaning more towards the carbon. But are the electrons physically transferred from the methyl to the carbon? No, never. The electrons never go from here to here. It's only that the orbitals, the field orbitals of CH3, they move towards the carbon. Basically, they're hiding it. They're hiding that electronegativity. Resonance, no. Resonance, you are moving electrons, right? From one side, C1, C2, C3, C4. You move electrons. Hyperconjugation, no. Hyperconjugation is only by, let's call it by induction, right? But it's an induction that is not stealing induction, right? It is actually an induction that helps. It's a donation, electron donating. Okay? So resonance is more stabilizing than hyperconjugation? No, definitely not. Those two totally separate things, but always resonance is going to be your best option. All right. So now that we know this, the hyperconjugation effect and the stability of the alkenes, so that's a very good starting point to start learning the reactions. Okay. Now, what if I can I create cycloalkenes, right? Because cycloalkenes can also be an option because I can have cyclohexyl chloride, right? So I can have a leaving group on a ring. Are they stable? Well, as it says here, in cyclic alkenes, less than 7 carbons, right, in the ring. So you always have to produce a ring that is stable. In this particular case, only cis alkenes are stable in 7 carbon rings. For example, cyclopentene, the H's are always going to be cis. In cyclohexane, the H's are always going to be cis. I know this is kind of a redundant, right, slide, but it's good for us to just to reaffirm that there is no way how we can turn. We cannot have a trans cyclohexene. So you will never have an H here and an H here. The H's will never be trans. Right? That's what I'm trying to say. You will never have those two trans. Why? Because there is not enough space for the ring to turn. To have them trans, you need to make a curl in your ring, and there is no space. There is no atoms in cyclohexene, cyclopentene to make it a turn. So only you can have it in carbons. Rings that have 8 or more carbons. For example, cyclooctene. Cyclooctene is big enough. Something similar to my, something like, if I wanna show you, right? So for example, this ring, right? So, well, here, let's say that one is as 6-member ring, let's say, right? So this 6-member ring, there is really no more options to rotate. I cannot really fold it, right? So there's not enough space. So if I have 2 groups here, they will have to be cis. Even if I try to fold it, there is not enough room for me to get them trans. But what if I have something like this? But now I have a necklace, something bigger. Of course, now I have more options to make it cis and trans, right? I'm playing with my ring, right? So imagine like a ring like that. So 8 carbons, definitely they make me more room. So here is a 3-member ring, but now I have 7, 8 carbons. Now I'm expanding the option. So I can make a curl here. So I can now get hydrogen strands. Where is the hydrogen trans? The hydrogen trans will be here, one hydrogen trans, and then here another hydrogen, right? These 2 hydrogens will be trans to each other just by making a fold in the ring. So basically that's what happens in rings that are 8 or more, that we can manipulate it so that the groups are, the hydrogens have the option to be trans. But very unlikely that we will see that, but that is for you guys to know that cis only. Cyclobutene, cyclopropene, cyclopentene, and cyclohexene, they're only going to be cis. There is no way how they can be trans. So we don't need to indicate if the alkene here are cis or trans. Yeah, I don't need to say here, for example, cis cyclohexene. No, you don't need to say cis cyclohexene. because cyclohexene has to be cis. There's no other way how it cannot be cis. Regioselectivity of E2 reaction. Okay, so here we're getting a little bit deeper on the reaction. This one is more or less about the, remembering SN2 reaction, we were seeing full inversion. This one is the stereochemistry of the E2 reaction. There are two options. This is regioselectivity. Okay, so what is regioselectivity? Okay, so there's Hofmann and Zaitsev. Okay, so nothing, this one is better explained by hand. Regioselectivity. Give it some few seconds to focus. Regioselectivity in E2 reaction. Okay, so remember that in the mechanism, right? So we had here, let's say here had a chlorine, right? We are doing an elimination reaction. We have to look at the beta hydrogens. What are my beta hydrogens? Here, here, here. And the other one is here and here. Those are my only beta hydrogens. This one is an alpha hydrogen. This one is a gamma hydrogen. I don't do elimination with those. I only do elimination with these 5. Okay, so if I use a base, let's use a strong base, right? Because remember, we're doing E2 reaction. I'm going to eliminate any of those hydrogens. These 3 hydrogens, right? So they are going to give me 1 alkene. That's the alkene that I will get. That is this carbon and this carbon are right here. And this will be right 1, 2, 3, 4. And if I eliminate this hydrogen, I will get that alkene. Oh, professor, you're also going to get the trans? Yes. Sorry, the cis? Yeah, you will also get the cis. Okay, so right, because you will definitely, you get the here in between. The mechanisms we will see in a minute, right? So don't get too confused about these two. How do you know that you're getting cis or trans? That's coming in a second. Now, I just want to tell you about the regioselectivity of the reaction. If you eliminate these beta hydrogens, you get that product. If you eliminate these beta hydrogens, you get these 2 products. Now, regioselectivity is about this. It's like which of the 2 sets is more stable, this one or this one. If you look at the product, this alkene is monosubstituted, and these alkenes are disubstituted. According to our previous slide, which one is more stable? The one that have a higher substitution. These are called the Zaitsev alkenes. It's the Zaitsev rule. Zaitsev rule says that in an elimination reaction, you always prefer to form or to produce the most substituted alkenes because they are more stable. So in this case, chlorine has the option to eliminate with 2 hydrogens, like 2 sets of hydrogens, right? The one on the left and the one on the right. Which one am I going to eliminate? I'm going to eliminate always the Zaitsev. The Zaitsev tells me like, okay, so if you're going to produce an alkene, well, produce the most stable, right? Don't produce the least stable. Okay, so this one will be my most stable alkene because it gives me the disubstituted alkene. If I do it this way, I will be producing the mono. The mono is not as stable. So the Zaitsev rule says that you always have to produce the most stable alkene. What is the name of this guy? This guy is called the Hofmann alkene. Okay, why is it the Hofmann? Or you could also call it anti-Zaitsev, right? It's the opposite to Zaitsev. So Hofmann, it is an alkene that is formed with the least substituted, right? It's the least substituted alkene that is forming an elimination reaction. Now, why am I learning this Hofmann if I know that Zaitsev, right, says that you always form the most stable alkene? Because there are a few exceptions. There are a few bases that do Hofmann elimination. Who does Hofmann elimination? Terburoxide. Terburoxide is the only, there are many, but that's the only one that we're going to be learning. Terburoxide is the only base that is going to be making the Hofmann elimination. Okay, so if you tell me this, for example, I'm going to make a cyclopentene with a bromine. Okay, I'm going to make it like this. If I mix it with ethoxide, okay, I know ethoxide is a strong base, therefore it's going to do an E2 reaction. So what are my possibilities here? What are my beta hydrogens? Okay, Navarro, you have beta hydrogens here too, and you have beta hydrogen here. Okay, great. Those are beta position. This is alpha. This is beta position. So I can make alkene here or I can make alkene here. Those are my two options, right? If I make the alkene on the top, right, I will make this alkene. If I make the alkene at the bottom, right, or the vertical, I will make this alkene. Which of the alkenes is Hofmann and Zaitsev? This one is the Zaitsev, because this alkene is trisubstituted. And what about this one? This one is disubstituted. The alkene, I'm talking about the alkene is disubstituted. So this one is my Hofmann alkene. Hofmann product, right? Ethoxide is a Zaitsev base, meaning that this one is going to be a minor product. Here is my major product. Okay, good. Let's do another case. Chlorine here. Okay, that compound. And now they give me terburoxide. Terburoxide is a Hofmann base. Okay, that's the only Hofmann base that we're going to be studying. So what are my options here in this compound? What are my possible alkenes? Well, I can form an alkene here. I can form an alkene here. And I can form an alkene here. Okay? Those are all my three beta positions, three types of alkene. Okay, let's make the one here at the bottom. The other one on top. And the other one. Those are the three alkenes. I'll do a different color. So that's the alkene in red. It's right here. The alkene in blue will be here. And the alkene in black will be here. So those are the three alkenes I will be producing. Which of them is my Zaitsev alkene? Well, I have here a trisubstituted alkene. Okay, here trisubstituted alkene. So they are both tri. What about this one? This one is disubstituted alkene. So the minimum, right, is the one that it is my Hofmann product. What about these two that are three? They are both Zaitsev. But what base are you using? I'm using terburoxide. Okay, terburoxide means that you are producing regioselectively, right? Remember, regioselectively, you're producing the Hofmann, the least substituted, because you're using the terburoxide. Terburoxide prefers always to do the least substituted alkene. Anything else is Zaitsev. Okay, so does that mean that you're going to be producing 0% of each? No, no, no. It's a percentage, right? So major product, we're talking about, well, 60% or more. This one maybe is 20-20, 20-20%, 60%, right? Something like that. You get the distribution of products, but that one is the major product because it's the Hofmann elimination. Now, I'm going to explain why terburoxide is a Hofmann base, right? So that's very important for us to know. Why is it a Hofmann, right? Why makes it like to cancel or to not to follow, right? Not to obey the Zaitsev, right? So definitely makes sense, thermodynamically speaking, that you form the most stable alkene because of the enthalpy of formation, right? Thermodynamics. But what about in the Hofmann? So what happens in Hofmann? In Hofmann, you have this chlorine, right? And you have these beta hydrogens. Those beta hydrogens are the Zaitsev hydrogens because they're more internal. These are the Hofmann hydrogens. Hofmann, because if you eliminate here, you produce this alkene. If you eliminate here, you produce this alkene. Okay? If you eliminate here, you produce that alkene. If you eliminate here, this alkene. So that's the Hofmann. Right? Clearly, this is my Hofmann elimination. This one is the Zaitsev elimination. Now, what happens with terburoxide? Why terburoxide only produces or regioselectively produces the Hofmann, the least substituted? Because the Zaitsev, right? You see the size of terburoxide. Terburoxide is a big guy. It's big, right? So it has a big frame. So it's really bulky, has 3 methyl groups, has the OH plus the hydration, right? The hydration layer. So terburoxide is too big to approach the the hydrogen that has to be from behind, right? It's too big. So if you have here a methyl, so you have something, some of the groups, it makes it even more difficult. So for a guy like terburoxide, it's easier to eliminate a hydrogen that is more exposed. It's hindrance. Everything is hindrance, really. Terburoxide has an easier way to eliminate this because of the nature of the base, not because of the strength. It's a strong base, but it's only by it's strong, but also bulky. So being bulky really has limitation for a base. So the base will have to eliminate now the most accessible hydrogen. The most accessible hydrogen is going to be a terminal, but a terminal gives you a Hofmann alkene, which is not that stable, but it's stable for the terburoxide because that's the only thing that it has available. Terburoxide is too big to fit on the back to produce an alkene this side. Okay, so that's the reason why terburoxide and any other base really that is bulky bases, they have to be bulky bases. This is a slide coming up that shows you all the example of bulky bases. But that's the idea, that the bulky base only has the option to access the most accessible, right? The most available, the most exposed hydrogen. So that one takes you to the Hofmann product. Hofmann product, not the Zaitsev. Zaitsev is you do it with ethoxide. Why with ethoxide? Because ethoxide is small enough to go back, and that's the attack. Same thing with methoxide. Same with hydroxide. Those are Zaitsev bases because they are relatively small. Relatively small. Okay, so because it always is about size, but if you compare with something. All right, so here, let's go back to the slides. We have the ethoxide, right? So it's a strong base, it's an E2 reaction, Zaitsev product 71%, Hofmann product 29%. See, there is a distribution because here, technically, you can produce 3 different alkenes. Okay? Where are those 3 different alkenes, Professor? The 3 different alkenes are here. One here, one here, and one here. Those are the 3 alkenes because I have 3 beta hydrogens. So I can produce those alkenes. But those 2 are the same. Methyl here, methyl here. So those 2 will be the same alkene. So technically I can also produce, I can only produce 2 alkenes. Right? One with those 2, which are equivalent, they're the same, and then here. That will be the second alkene. So that's what we see. Zaitsev product and Hofmann product. Okay? So 71%. And this one is Zaitsev, is a major product because I'm using ethoxide. Ethoxide is a Zaitsev base. Okay, so the Zaitsev product is the one that produces the more stable alkene. The more stable alkene is the one that has the higher substitution. Okay, here's another example: ethoxide, regioselective, 71%. Right? I mean, it's the same example. It's only just repeating. The reaction is regioselective, meaning that it gives you in major proportion. There's a difference between regioselective and regiospecific. Specific means that it gives you a unique product. For example, SN2 reaction is stereospecific. It gives you 100% inversion, nothing of the retention. That is specific. That's being specific. Here is selective. Selective means that it will give you a major product only for that particular conditions. The other one is also produced, but in less percentage. Okay, so there's a difference between being selective and being specific. Okay, so the regioselectivity of an E2 reaction can be controlled by choosing carefully the strong base. Yes. So if I use a Hofmann base, for example, terburoxide, I can reverse these percentages just by changing the type of base. Right? So this 71 and 29. So here's an example. Okay. So I have the same substrate. I have this alkyl bromide, right? This bromide, the name for this bromide will be 2-bromo-2-methyl butane. That would be the name for this compound. React with different bases. That's terburoxide. Right? You see terburoxide, it gives you more Hofmann elimination, 72% versus 28%. What happens if I make the base even bigger? I don't know the name for that, but it looks like a virus, right? Well, I mean, the structure of a virus in bio. The bio people can definitely associate it with the virus when you guys draw viruses. Right? Something like that. You represent viruses like that in bio. So the base, which is very bulky, you see, it makes you even a higher Hofmann. Why? Because it's too big. There is no way you can produce the most stable alkene. It's too hindered. It's too secluded. It cannot reach. What about ethoxide? Ethoxide is very small. Ethoxide 71% versus 29% size F bases. So what are the most, the most common bases? Well, the most common bases you guys will see in the books and exams, PCAT, MCAT, any exam where you guys want to be taking ethoxide, methoxide, hydroxide, and terbutoxide. But technically, it should be any small base or any bulky base. And then we can use as a cutoff terbutoxide. Terbutoxide would be the alcohol, or sorry, the base that is big enough to give you major Hofmann. Anything bigger than terbutoxide should also give you Hofmann elimination, right? Hopefully that idea is clear. These are some other examples for bulky bases, right? So diisopropylamine, that's another one. I don't know if they call this DIPA. Yeah, maybe they call it DIPA. Triethylamine is another base that is very bulky, right? That, and then potassium terbutoxide. Normally I drop, you guys will see that the potassium is silent, right? You just call it terbutoxide, which could be potassium terbutoxide, sodium terbutoxide, anything. But really the one that is the base is the potassium terbutoxide, sorry, the terbutoxide, right? Terbutoxide is the base. We already explained, right? This one, the Hofmann product, right? Those are the non-nucleophile. Okay, here's a good practice. So let's see. I'm gonna redraw these molecules and then we will practice together. This one is, of course, in addition to the solve problem videos that are also available on Blackboard. Okay, so here I have chlorine and just redrawing this ethoxide. The second one is with terbutoxide. And sorry, sodium hydroxide, and the last one is terbutoxide. Okay, so let's go over these problems. All right, let's focus by itself. Okay, so this particular example, they give me a ethoxide. So when you guys are doing E2 reaction, please make sure that you identify what is your carbon that has the leaving group. That's going to be one of my carbon alkene. One of my alkene carbons is here. So now, where am I going to be making the alkene? Well, I can make the alkene here, or here, or here, right? Because those are the beta positions respect to my alpha carbon. So if I make it here, the alkene would be disubstituted. If I make it here, the alkene will be, oh, here I cannot make it. See, that's a good thing. Why? Okay, so I made a mistake here. Why I cannot make an alkene here? Because there is no beta hydrogen here. There is no beta hydrogen. So you see, this carbon has CH3, CH3, CC. So there is no hydrogen. How can I make an alkene if there is no beta hydrogen? No beta hydrogen. I only have two possibilities. What about here? Here I have beta hydrogen, so I can do an E2 here. If there is no beta hydrogen, there is no E2. You need to have beta hydrogen. Okay? So if I do the alkene here, I will have disubstituted. If I make the alkene here, I will be trisubstituted. So I'm going to draw both products. Okay, so my both products would be, that's one. Okay, that's the other one. That's this alkene is this alkene, and this alkene will be this alkene. This is disubstituted, and this is trisubstituted. I'm using ethoxide. If I'm using ethoxide, I have to use the Zaitsev rule. That is the Zaitsev. That will be my major product. Do I have to draw both? No, you only have to draw the major product. Don't draw the minor product. I'm just doing this too just for our analysis. But really the product that should only be displayed is this one. That's your major product only. It's ethoxide. Ethoxide is a Zaitsev base. And now, of course, I'm E2 reaction because this is a strong base. Should I look at it if it's tertiary, secondary, primary? No, you don't have to. You only have to look at the base, if it's strong or weak. Strong, E2. And then after you see it's an E2 reaction, then you go, it's a Zaitsev base or a Hofmann base? It's a Zaitsev base. So I have to produce the most stable, the most substituted alkene, right? Here, for this one, I have sodium hydroxide as my base. Okay, so in this case, I have two potential alkenes, here and here. Here you say, oh, what about this one, professor? It's the same because it's methyl. Methyl, they will both produce the same alkene. So if I make it here, that would be one, the first alkene, like that. Plus, if I make it down there. Okay, Which one is Hofmann? Which one is Zaitsev? This one is substituted, substituted. This one is the Zaitsev. And OH is a side-safe base. So this one should be a major product. Here, the last one is butyroxide, right? Now here is the same. So I'm going to be producing both, again, both alkenes. But which one is my major product? Okay, your major product is going to be now you're using a Hofmann base. Using a Hofmann base, you have to produce it substituted. This one is your substituted. This one will be your major product. Okay, good. So that's the way how to do the reaction. Now, we didn't really go over the mechanism. I'll show you how to do the mechanism of a general E2 reaction. How to draw it, right? So without the stereochemistry. Stereochemistry of the E2 is coming next, but just a general E2 reaction. I'll just tell you ethoxide. This one, ethoxide is a Zaitsev base, therefore it's going to eliminate one of these two hydrogens. Right? So the mechanism would be ethoxide, oxygen of the ethoxide attacks, steals the hydrogen. This bond comes up to form an alkene, and this one leaves. So the result would be that this alkene. Now you could say like, oh, professor, how do you know if you are producing cis or trans? Okay, now since I'm telling you now this mechanism, the mechanism of the E2. Okay, if you have an E2 reaction, right? If you have a CH2, two beta hydrogens available, these both are beta hydrogens. One of them is going to produce the cis, and the other one is going to produce the trans. Okay, if you have two beta hydrogens, one will give you the cis product, and the other one will give you the trans product. But do I need to know? Is there any way how I can tell if this one is going to give me beta 1 is going to give me the cis, or beta 2 is going to give me the trans? Yes, there is a way how you can do it. That's why we use Newman projections. But if you have two H's, two beta hydrogens, you don't need to. Why? Because you know that one is going to be cis, the other one has to be trans. You only have two options. You only have two hydrogens. Between the cis and the trans, which is more stable? The trans is more stable. So no matter which hydrogen you eliminate, you know that always the trans is going to be your major product. You always know that because it's the trans. Am I going to produce the cis? Yes, you're also going to produce the cis, but the cis is going to be my minor product. No matter what, it's always going to be the minor. So why do I need to spend time figuring it out, right? To figure out which one is cis, which one is trans, if I know that my major is always going to be trans, right? So whenever you guys do elimination mechanism on a need with a carbon that has two beta hydrogens, then just write the trans product. Don't spend time. What should I do if I only have one beta hydrogen? What if I have only one beta hydrogen? Now, yeah, now it changes. If you have only one available beta hydrogen, now it's a big question mark. Am I going to produce the trans, or am I going to produce the cis? Now, I don't know. At least here, you have two beta hydrogens. One has to be the cis, the other one has to be the trans. But no matter which one is which, the trans is always going to be the major. Here, no. Here, you only have one hydrogen, but you don't know if it's going to make the cis or if it's going to make the trans. Then how do I figure it out? You have to do Newman projections. Okay, so that's the only way how you can tell if this one is cis or it's going to give you a trans alkene. I'm saying cis and trans alkene, but what I really mean is that if you're going to get an E alkene or a C alkene, right? They both E trans or C cis alkenes, right? Oh, professor, what about the one what if I have three hydrogens available? Yeah, you have three hydrogens available. Don't worry. Actually, it's easier. Because if you have three hydrogens available, that means that your alkene is going to be terminal. It's going to be this. So does it matter which one I eliminate? No, because you always have two hydrogens terminal. So there is no way you can tell that it's not going to be EZ or cis and trans because you have two hydrogens. It doesn't matter which one you eliminate because your alkene is terminal. So don't worry about if you have three alpha hydrogens to know the stereochemistry. If you have two beta hydrogens, that doesn't matter because you know that definitely one is going to be the E or trans is going to be the major product. But if you have one, yes, that one you need to do something else, right? So that's just about the mechanism, but the mechanism is like this. Ethoxide attacks the beta hydrogen goes up, right? The bond goes up to form a double bond, and the leaving group leaves. So the iodine is lost in this particular reaction. All right, so let's continue. All right, so that's exactly what we were talking about. Stereospecificity of E2 reaction. Consider the dehydrohalogenation. Oh, that is just a complicated way to say, consider the E2 reaction of the alkyl halide below. There is only one beta hydrogen to be removed for E2 elimination to occur. Is it gonna give me the E alkene? Is it gonna give me the Z alkene? I don't know. So I have to use the Newman projection, right? So there are many slides here. Here it says, I mean, here already it's telling you there is this reaction, right? There is this reactant, and you get only one product. What type of alkene is this? If I mean, just go back to chapter. We did this on chapter 5, right? Alkenes, easy. I think so. When we were doing RS, we also did easy. Chapter 5. This one will be my highest priority, and here will be this one highest priority. This one is an E alkene. If this E alkene is observed, and you don't get this one. This one will be the Z alkene. You don't get this one. That is called stereospecific because you only produce one product. You don't produce major minor. You only produce one product. Okay? So here, this particular compound is telling you that with sodium ethoxide, which I know is a Zaitsev base, E2 base, it gave me only E alkene. How come it give me an E alkene and no C alkene? So we have to go through the Newman projection here, and then here is what we call the anticoplanar transition state. That's what happens in an E2 reaction. The anticoplanar means that the H and the bromine are totally opposite, the farthest away you can place them. How can I get this anticoplanar? In a Newman projection, you will find the anti position. H and Br are separated by 180 degrees. Is the maximum separation you can have. So how is the mechanism working? You have a base. The base attacks the H. This bond comes here to form a double bond, and the bromine leaves. That's how it really happens. That is how the transition state really works for E2 reaction. Okay, so now how to do this Newman projection, how to do the determination, that's going to be coming soon. I'll do it on paper. Okay, so this one is a procedures. I mean, you can read this slide, how to make the alkene from the Newman projection. But I mean, I'll do it. I mean, it is just for your reference. This one is about the difference between stereospecific and stereoselective reaction, right? Something that we were emphasizing. Stereoselective means that it will be a major product out of 2 or 3 options, whereas stereospecific, there is only one option, which is the one that happens. Okay, so let's stop this, and let's do this. What to do if you have one single hydrogen. Okay, so let's say that they tell me, okay, so you have this particular leaving group, bromine, okay, another methyl. Of course, the camera doesn't focus when I need to. Here we have a cyclopentane and hydrogen. Okay, so they tell me do the E2 reaction in the presence of ethoxide. Well, they don't need to tell me E2 because I know that ethoxide is going to be an E2 reaction, right? E2 reaction, I know it's a Zaitsev. So according to Zaitsev, I have to produce the most stable alkene, meaning the highest substitution. Here, I can produce a beta. This one is my alpha hydrogen. This one is my beta beta, and beta. These betas are terminal. Therefore, they are not going to be Zaitsev. This one is internal, right? Because there is more. There are more carbons next to it. So that one will be my Zaitsev carbon. And that Zaitsev carbon only has one hydrogen. If it has only one hydrogen, I don't know if it's an E or a C alkene. I know that the base will come, take the hydrogen, this bond will come down here, and then the bromine, right? So I know that mechanism because we already went over that. But I don't know if it's going to be methyl. Let's change this by a methyl. Oh no, let's make it a hydrogen. My bad. Let's make this a hydrogen. Okay. So that's still, yeah, because it will be disubstituted. Yeah. So you still get the same. Here the same. This one is still your Zaitsev, size F point. This one will be the size F, and this one will be your Hofmann hydrogen right here. So Hofmann product alkene. You can produce two alkenes, one here and one here. Those are your two only options, right? You cannot do it here because now it has a hydrogen. So these two here. This one, if you produce an alkene here, it will be disubstituted. If you produce alkene here, it will be trisubstituted. So definitely you have to produce it trisubstituted with an ethoxide because it's a size F base. Okay, so how to start? Okay, so we have to construct the Newman projection. You can do the Newman projection looking down here or up here. That doesn't matter how you want to do it. So I will do it from here. You can do it from the bottom, that's it. If I look at this from this side, I will look the carbon like this. Bromine is sticking out. So if my eye is here, bromine is going to be sticking out. That's going to be my, right? So it's something like this. Right? So bromine is wedge sticking out. If I put it on the paper, it will be on the right side, bromine here. Hydrogen is a dash. If I put it on the paper, it will be on the left. This ethyl is pointing down. Now the one on the back. That's a stagger, so that's good. Has to be staggered anyway. So the hydrogen is sticking in, right? This hydrogen is a wedge. And the cyclopentane is a wedge sticking out. So if I put on the paper, cyclopentane here, hydrogen here. We're gonna abbreviate it with Cy P, cyclopentane. And the other one is a methyl up. Okay, so which is the hydrogen that I have to eliminate? It has to be a beta hydrogen. Say, oh, professor, I see two hydrogens. Can I eliminate this hydrogen? No, because that's an alpha hydrogen. It's the same, this hydrogen is attached to the same carbon as the bromine is. So this one cannot be the beta hydrogen, that's the alpha. The beta hydrogen is this one. And it happens that in this case, the beta hydrogen and the bromine are anti-coplanar. They happen to be 180 degrees already apart. So what am I going to do? Simplify your lives. Once you guys see that your H and your bromine are anti-coplanar, all you just have to do is just to do an alkene in the middle. Put the alkene there. Why? Why is that? Because if you put the alkene, everything will be translated into the alkene. H, right? You see, these guys are gone. And alkene is in between. So you see the alkene H, right? Down ethyl, up methyl, and here cyclopentane. Okay. Why? Because in the is the triangle, right? The triangle has the hydrogen and the ethyl here. The circle has the methyl and the cyclopentane, and that's its relative position. What is this type of alkene? This one is a C alkene. So you produce the C alkene here in this particular reaction, right? One more. Let's see, another one. OTS. methyl and ethyl. Yeah. Okay. They tell me this one is under methoxide and determine what is the alkene that is a product of this reaction. All right, great. You tell me do the alkene. I know that a methoxide is an E2 base, strong base E2, and also I know it's a Zaitsev. If it's a Zaitsev, I have to choose the most stable alkene. If my leaving, that is my alpha carbon, right? OTS is my leaving group, is attached to this one. This is my alpha carbon. I could form an alkene here or alkene here. Out of the two, this one is my Zaitsev alkene. This one is the Hofmann alkene. How do I know that? Because this one is a terminal alkene, and this one is an internal alkene. So I prefer the internal. That's the Zaitsev. Okay, that would be the Hofmann. Okay, great. So convert this into the Newman projection. Here, let's look at from bottom to top. Okay? So if I look at the bottom to top, I will see this. On the here, right? It will be like this. So the methyl is sticking out and the OTS is sticking in. If I put it on paper, it will be here on the left, methyl and OTS. Here, hydrogen on top. Okay, good. That's the front carbon. The carbon in red would be the circle. Methyl is on the left, right? The same as the, sorry, ethyl is on the left, the same as the methyl. Ethyl here. Methyl and hydrogen down. Okay, what do I have to eliminate? I have to eliminate this hydrogen with this OTS. Not this one, because this one is an alpha hydrogen. This hydrogen is attached to the same carbon as the OTS. So you cannot make an alkene here. They attach to the same carbon. It's impossible. So you have to match this H here in red and the OTS. But they are not anticoplanar. They are not anticoplanar. What should I do? I have to rotate as we used to do before. Remember the eclipse, staggered eclipse, staggered eclipse. You have to do the same thing until I get this guy's anticoplanar. What I'm going to do, I'm going to rotate the pencil structure. I put the OTS now on top, the H, right? I'm rotating counterclockwise. If I counterclockwise, OTS up here, H down here, and methyl here. The back, no change. I should not move the back. Okay, now I have the leaving group and the H anticoplanar. Now all I do is just put the alkene in the middle. So what is the alkene that I'm getting? Okay, the alkene that I'm getting is on the left, hydrogen, bottom left, right? Bottom right, methyl. Top left, ethyl. Top right, methyl. What type of alkene is this? Methyl ethyl. This one is an E alkene. Once again, if you guys don't remember how to label E and Z alkenes, please go back to chapter 5. It should be on chapter 5 about stereochemistry. I'm sure it is in chapter 5 about how to label E and Z alkenes. This one is an E alkene. I only need to do this for if you have only one available beta hydrogen here. Only one. If I have two, of course, one is going to give me the E alkene, the other one is going to give me the Z alkene. And definitely, I will prefer the one that has the least steric hindrance, right? The one that has the groups, the bulkiest groups, right, opposite each other. Okay, great. So let's go back to the slides. Basically, that is all that is explained in the in those previous slides. Now, what to do with chairs? Chairs is a very, very important, also very important chapter. Okay? So in the case of chairs, cyclohexanes, right? Now we are dealing with axial equatorial. So now what should I do? So the only way that you can have an anticoplanar configuration, right? Remember the anticoplanar, the one that we did right here, the anticoplanar, what is it? Oh, here. Here's my anticoplanar. The only way how I can have an anticoplanar in the 6-6 member ring is by having the groups axial. You see, axial up or axial down. What if I have the equatorial up and equatorial down? No, you cannot do E2 reaction. They have to be available. They have to be able to be diaxial, right? So, for example, here, elimination can occur in this chair conformation. Why? Because the chlorine is axial. Here, no, because the chlorine in my living group is equatorial. But I need to work with that equilibrium. That's why here it says clearly, even though the equilibrium favors the equatorial substitution, right? But you still have a little bit, right, from the axial. So you need to be able to manage between the equilibrium of the two species. Okay. So how to deal with this chair, right? The chair issue. So the best way is to use the cis and trans. Okay. So for example, in this slide, asking you like which of the two molecules will not be able to undergo an E2 elimination reaction and why. Right. So remember that in the previous slide, one of them had to be axial up and axial down, right? To be anticoplanar. Axial up, axial down should definitely ring a bell. What is that bell? The bell is that they have to be trans. The alpha, the living group and the beta hydrogen have to be trans. Where do I see that? For example, here, the chlorine is a wedge, and here the hydrogens are dashes. So these guys are trans to each other. So that means that here I could potentially form an alkene between these two. I mean, not between these two, right? By using those two. Here, the same thing. Do you think that I can form an alkene between that H in triangle right here and the chlorine? No, I cannot do an alkene there. Why? Because they are both cis. A beta hydrogen that is cis to a living group is never going to do elimination. Okay? But we need to be clear here. So can I do elimination with the red hydrogens? Yes, you can do it. What about here? Okay, the chlorine is cis respect to the beta hydrogens. So here I can do elimination. There is no elimination. So which of the two molecules will not be able to undergo an E2 elimination? This one will not be able. Why? Because the beta hydrogens and the leaving group are cis to each other. It might be helpful to draw a chair conformation. Yeah, I mean, it is, but I mean, with the trick I just told you, I mean, that's enough, right? I mean, definitely you see the chair, definitely you can see it, but just by using the cis trans, right, convention, you can definitely determine if a beta hydrogen can be eliminated or not. Okay, so this product, this one is actually a very interesting example. And expect something like this question in the exam. This reaction, right? So E2 reaction is slow. Only one product is formed, this reaction. And here E2 is fast, and then you see two products. We have to explain why. Okay, so let's do that. So I'm gonna let me draw that problem. You have the Cl, ethoxide. It doesn't matter, methoxide, but it's ethoxide. This is low, and we only get one product, butanol, alkene here. And the second reaction, you guys have the chlorine wedge with the tributanol, tributyl, also ethoxide, fast, and you get two products. Okay. We have to explain why. All right. Okay. So this reaction, they say, is very slow. Okay. Why is that? Let's see. In this case, yeah, I do need, for example, in this case, I have to identify what are my alpha hydrogens, right? My alpha hydrogen, sorry, beta hydrogen. Beta hydrogen, I see a beta hydrogen right here. That is trans respect to the Cl, right? Remember, it has to be trans. Here, the hydrogen is not trans, it's a cis. So this guy cannot be eliminated. So forget about this one. The only one is this this beta hydrogen is available because it's trans respect to the chlorine. Okay, but they tell me that the reaction is very slow. Yeah, the alkene is formed when I'm supposed to see it, right? The alkene should be here, formed between here, I mean the hydrogen and the chlorine. Yeah, that's fine. But I have to explain this slow. How can I explain a reaction was slow or fast? In that case, I do need to do the chair conformation. Okay? So let's do the chair conformation for this particular compound. That's the chair, not the best, but a chair. Okay, the first group that I have to put terbutyl. Why? Because terbutyl is the Barkes group. Up, equatorial up. I need that terbutyl, equatorial up, terbutyl right there. That is that carbon. Let's go clockwise. Next one, chlorine. Chlorine down. Okay, chlorine down means chlorine here. Next, okay, hydrogen's there. The other one is empty, empty, empty. Okay. Okay, now I see why it is slow. Because the chlorine is occupying equatorial position. What is the problem with chlorine occupying equatorial position? That it cannot undergo E2 reaction in equatorial. I need it axial. You say like, okay, not a big deal, right? If it's equatorial, you need axial. Well, all you have to do is just is flip the chair. Right? Whatever is equatorial becomes axial. I flip the chair, I send the chlorine axial down, and this hydrogen will be axial up. Now they are anticoplanar, no big deal. It should be okay. Yes, but remember that the flipping is also going to flip your terbutyl. The terbutyl here is equatorial. If you flip it, the terbutyl is going to be axial. And terbutyl axial is the worst. It will be like an arrow this way, this is small, and then it will be this way, that big. So it's going to be a very small percentage. 0.001% is going to be in the flipped chair, which is what you need for the E2 reaction. That's why the reaction was very slow, because it only a very small portion of this chair flips. It's going to flip in a very small percentage at a time. So even though you do the reaction, but you will only be consuming 0.01%, let's say in a minute, right? That's why the reaction is very slow. Let's see here. It says that the reaction is very fast. Okay, so which one are my alpha hydrogens? Sorry, beta hydrogens. So here I have a beta hydrogen that works. Yes, it's trans respect to the chlorine. And here also another one that works. They say that the reaction is very fast and I get two products. Okay, apparently you are getting the product with both hydrogens, right? Alkene here, that's this one, and alkene here, which is this one. Okay, so now let's see why is it so fast. To see if why or explain why is it so fast, you guys have to do the chair conformation. Horrible chair, but a chair. Okay, first one to be placed, terbutyl. Terbutyl is equatorial up. Equatorial up, terbutyl. That one goes here. Clockwise, next one, chlorine. Chlorine now occupies axial up. Perfect. That's what I need. Next one, hydrogen down. This hydrogen is down right here. Next one, nothing. Next one, nothing. Nothing, nothing. Okay, good. Why is this reaction going so fast? Because the chlorine, the hydrogens to be eliminated, which are these two hydrogens, right? They are anticoplanar, anticoplanar. They call it anticoplanar, but you will also see anti-periplanar. Periplanar, coplanar, both of them I have seen. So just don't be, right? If you see periplanar, works also, coplanar. The book is uses coplanar, but I read it also periplanar. Okay. the chlorine and the beta hydrogens are already diaxial, axial up, axial down. And then this one is favored in 99.9%. The other one is only 0.1%, even less, 0.01%. So this one, that's why the reaction goes so fast. Why? Because the chair is already in a configuration that allows the chlorine and the hydrogen to be anticoplanar. So the reaction just proceeds, right? So without with any other problem. And then it can populate both because it has two hydrogens that can be eliminated. It doesn't tell you which one is the major and the minor. I would say that the major product should be this one, right? Why is that? Because this one is a trisubstituted alkene versus this one, which is a disubstituted alkene, right? So that one should be your major. That one is your Zaitsev, and that one will be your Hofmann. You get both, right? But of course, the Zaitsev is the major product. That will be your major product. Okay, so that will be an answer for the question to that slide. Definitely, we'll have more for the solve problem videos. All right. E1. Okay, so we're done with E2 reaction. Okay, so in E2 reaction, so far what we have done, just to brush up a little bit, I don't wanna end E2 without telling you that now we should be ready to do synthesis problems. What is synthesis problems, Professor? Synthesis problems are problems in which you guys have to accomplish a conversion, meaning that what do I need to go, for example, from let's say from this compound to this compound. Okay, so what do I need? Okay, so this alkene has to be made by elimination reactions, either E2 and E1. So far we have learned E2. Okay, so let's use E2. So if I look at the reactant and the product, right? So you might see that I have a group here. This one is a bad leaving group. That doesn't help me that much. So, but I see that I have a group here. So this group, if I need elimination, right? Elimination definitely need a substrate, which is a leaving group. So the alkene can be formed here, if it's Zaitsev, or here, if it's Hofmann. Right? According to my product, I see that the alkene is Zaitsev because it's on the left side, right? Giving me the most substituted alkene. Okay, so what am I gonna do? So this guy has to be converted into a good leaving group. How can I make an alcohol into a good leaving group? With tosylation, tosyl chloride in pyridine, OTS. That's my first step. Now, how can I go from this OTS at this substrate to this alkene? I have two options, alkene here or alkene here. I want the alkene here. Okay, that's the Zaitsev. What is the Zaitsev base? Methoxide. Methoxide in methanol. Normally it's a combination. You will see it alone or in a combination. Methoxide, methanol. That's a combination. They are both, they mean the same. Methoxide. Can I use ethoxide? Can I use hydroxide? Yes, any of them. So this one will give you that alkene. This is called synthesis. Okay? I'm introducing you to this one. I mean, right now, early stages in 7B, because you guys will see this a lot later on. Chapter 8, chapter 9, chapter 10, we will do synthesis problems all the time. Okay, so they will only give you these two starting materials, and you have to figure out what are the steps in between. This particular reaction has 2 steps. Sometimes it has 3, sometimes it has 4. Of course, as you get to know more chemical reactions, the number of steps might increase. But normally these synthesis problems, they have maximum 3 or 4 steps. So far, you only have 2 because you only know SN1, SN2, and E2 so far. But as you guys get to know E1, you get addition reactions, you get addition to alkynes, and you get to know also radical reactions. That array of reactions will increase. So your steps might also increase. Okay, but that is what we call synthesis. You guys are going to synthesize something. Synthesis problems, right? So that's a parenthesis of what is coming up, but that is the idea of what we are doing with E2 reactions. Okay, E1 reaction, even though it has 2 steps, but there is really less to discuss than E2 reactions. Okay? The reaction also needs the reaction. Let me change color something. It's a tertiary substrate. You also need a tertiary substrate. At tertiary, the trend also goes tertiary, secondary, primary. Okay, in an alcohol solvent. So it is an ethanol, right? So we say that the weak bases are alcohols in general, ROH, and water. It can be used as weak bases. So that's why here they tell you ethanol is a solvent. You can use ethanol, methanol, propanol, doesn't matter. It's a stepwise mechanism. And the first step is very similar to SN1 reaction. The first is the most difficult step is the dissociation of the substrate, the leaving group leaves, generating carbocation. Then the carbocation, this one is, that's why it's a unimolecular reaction, because the most difficult step only involves one molecule, which is the substrate. Okay, so once the substrate as dissociated, remember, anytime that you guys form a carbocation, there is a potential CCR. In this case, there is no CCR, but anytime that you form a carbocation, don't forget to always look for CCR. Once you do the CCR, then you do the nucleophile, the base attack, the proton transfer. So the base attacks the beta hydrogen. That's still the beta hydrogen. It's a beta hydrogen, and that bond comes down to form an alkene here, and that's the elimination product. Synthetically, from the synthetically point of view, is it like a very convenient reaction? E1? No, really. I mean, you might see it very, very rarely. The most one that is most applicable one is E2 reaction, because you have control. You can control Zaitsev, Hofmann, right? I can control C strands, right? So I can definitely, there's way many things to control in an E1 reaction. Ethanol is serving as a base, right? But it's also not a nucleophile, because it's attacking the beta hydrogen. It forms the carbocation. That's the same. That they have something in common, the SN1 and E1 reaction. But it's really now the water molecule is acting as a base. Here's the difference between the kinetics, right? So it's an E1 and E2 reaction. The alkene has more energy. It's less exothermic in this case. We can call it like that, less exothermic, because the alkene is more unstable than the, right? Because you are here, you have four sigma bonds. Here you have only 3 sigma, 1 pi. Sigma are more stable than pi bonds. That's really what explains why E1 has a higher energy than the SN1 product. But the first step is exactly the same: the dissociation, the formation of the carbocation intermediate, and then here you guys have the transition states for each of them, right? So giving you different products, but it's unimolecular, meaning that the most difficult step only depends on the substrate, which is the starting material. You don't use the base until very later. Our rearrangements, yeah, you have rearrangement in E1 reaction. The reactivity, we will do that in a second once we do the mechanism. Okay, I'm gonna go back to the rearrangements. The success of the E1, same as the SN1 reaction, depends on the efficiency of the leaving group. Iodides are good leaving groups, better than bromides, better than chlorine. Fluorine are not leaving groups, right? So use any of those 3 for leaving groups, in addition to tosylate and OH2 plus cannot be, I forgot to say that, you cannot use OH2 plus in E2 reactions. Why? Because to make an alcohol a leaving group in acid, you cannot have acid and base at the same time, right? So remember that you are using strong bases like ethoxide, methoxide, those are bases. So if you put OH2 plus, it's an acid. Acid with base, they neutralize. So they are not going to produce an alkene. What they will do is they will do an acid-base reaction. So when you guys need to activate or to make an alcohol into a good leaving group, don't use the acid treatment. Only use tosylation for that, right? I forgot to mention that in my synthesis problem. Only tosylation, iodine, bromine, and chlorine will be your leaving groups for E1 reaction. Okay? All right. Keep going. So E1 reactions, they can also, don't forget that you can have a resonance stabilization in the carbocation. The most stable carbocation will give you the best or the faster reaction, the faster E1 reaction, same as the SN1 reaction. For example, here I have a benzylic carbocation. This one cannot give me an elimination product. Why? Think for 3 seconds. Why this carbocation cannot do E1 reaction? 3, 2, 1. Okay, the answer is because this carbocation does not have a beta hydrogen. The only beta position is this carbon, and this carbon doesn't have beta hydrogens. What about this one? This one, here you have a beta hydrogen. But what happens with the beta hydrogen? Can I do elimination there? In that case, no, because it's in resonance, right? So that carbocation is, I mean, that beta hydrogen, if you produce it, it will give you this alkene, right? With the 2 double bonds. Yeah, that's very unusual. You don't see that much, okay? So just do E1 reaction in this conventional carbocation. But those carbocations are stabilized by resonance. That's why they are used. Nobody even mentioned this for solvolysis, which is SM1 reaction. But for our uses, the higher, the more stable the carbocation, for example, tertiary carbocations, secondary carbocations are preferred, right? Rather than primary carbocations, right? Because they are very unstable, as we know. Okay, so here we have an E2, E1 reaction. Yeah, definitely the only option for elimination would be right here, because here there is no beta hydrogen. So you guys use water and heat. Water is your base, as a weak base, definitely is an E1 reaction. Why heat? Because it is, this reaction is, definitely you need to apply heat in the sense that you are breaking, you're forming a pi bond. Right? So originally your starting materials, they all have sigma bonds. But now your product is going to have a pi bond, which has higher energy. That's why the reaction needs heat most of the time. For elimination, you need heat. Okay, stereoselectivity in E1 reaction. Yeah, there is a major product. Or E1 reaction always follows Zaitsev. I want to be very clear. Zaitsev only. You cannot do E1 reaction Hofmann Zaitsev. It's only Zaitsev. And here you can see that your major product is right here. That's the Zaitsev. This one is the Hofmann. These two are Zaitsev. Zaitsev, tri-substituted. This one is disubstituted. That's why it's Hofmann. Hofmann is a minor product. But between these two Zaitsev, why is this one a major product and not this one? 5 seconds for that. 5, 4. Right, very good job. The reason is steric hindrance. I have the bulkiest group for this alkene. I mean, for this carbon is right here, and the bulkiest group of this carbon is right here. The two bulkiest groups of the alkene are opposite. Here, the bulkiest group is here, and the bulkiest group is here. The bulkiest groups of both carbons are face to face. That's bad. That's why this one is my major product. Okay, that's the substitution. That's a minor product. So, but the major product is definitely that one with the alkene. Okay, E1 will give you the most stable alkene as the major product. Yeah, it's decisive. When two stereoisomers are obtained, the least sterically hindered. Steric hindrance is a major role here, right? Plays a good role in deciding what is your major product. Okay. Okay, great. So let's see now the mechanism. All right. So let's assume that I have this particular substrate. Okay. I'm going to put iodide, and then I'm going to put here an FO. And they tell me that I mix it with water. Determine what is the mechanism, right? Or the products. Okay, so to do the products, let's first do the products. Okay, so I know that is water, therefore it's going to be an E1 reaction. I know that the E1 reaction is always going to be Zaitsev, right? So that's the main issue. But the only thing that I have to be aware with E1 reaction is that this one can potentially give me CCR. Okay, you don't have to be concerned about that in E2 reactions. This one, yes. Okay, so what I'm going to do here is I'm going to dissociate it. The first step is going to be dissociating. Even for the for the reaction, you don't have to do it for me, carbocation. That's my carbocation. Right? Iodine is out, carbocation. I'm not doing the mechanism. I'm not doing the mechanism. All I'm doing right now is determining what is the product. But to do the product, I have to keep in mind that I can do CCR. So the only way how I can predict CCR is by creating the carbocation. I cannot predict the product just by looking at this. Because if I don't create the carbocation, then I don't know if I do CCR or if I don't CCR. I don't do CCR. I cannot predict it. I do the carbocation. Now I have to see if I can do CCR. Can I do CCR? Okay, secondary carbocation, primary carbon, tertiary carbon. Yes, I can do CCR. Where is the CCR going to go? It's going to go to the tertiary, of course. So my new carbocation, that's why it's so important. My new carbocation is going to be here. That's my real carbocation, right? So what are my beta hydrogens? My beta hydrogens are, or my beta positions are here, here, and here. Those are the three beta positions. If I do it here, what would be my beta positions? My beta positions, I would say, would be here and here. And they are wrong. They are not my beta positions. My real beta positions are this one, because they happen always the beta position after CCR. Okay, now that I have CCR, now I have to determine which one of them are Zaitsev. Because Zaitsev is right, is E1. This one will give me a secondary, like that's substituted alkene. If I do it the one on top, I will get that. If I do the one at the bottom, I will get that. So disubstituted, trisubstituted, trisubstituted. These two are Zaitsev. This one is Hofmann. Hofmann, Zaitsev, Zaitsev. Now, out of the two, is there any difference? Not really, right? They are the same. They're the same. I mean, they are isomers, right? No, they are diastereomers, right? They are diastereomers because they are cis trans. The methyl here are cis, and here the methyls are trans. So basically, they are the same. Okay, so that means I'm gonna do it with this. My product would be, let's say, like this. Okay, that is my product. Now the question is, now write the mechanism for that. Okay, the mechanism is different. That one I have to show step by step. Okay, they tell me draw the mechanism for this conversion. Mistake. We said that the other one was the major product. Okay, right? We said that this was the major product. Right. Good. First step in the SN1 reaction. Sorry, E1 reaction. Dissociation. Okay, after dissociation. This compound undergoes CCR, right? I have here the hydrogen. I do a hydride shift towards the carbon. Now I have a carbocation, right? CCR. Good. Now comes the water, the base attack. So the base, of course, is going to attack that beta hydrogen, right? Because the alkene is right here. So definitely has to be on that hydrogen. The water attacks the hydrogen, and this one comes down to form the alkene. Now here, there is no anticoplanar, there is no 180 degrees, there is no Newman projection. You don't need to do Newman projection here. Okay? So water attacks the hydrogen and then comes out. And that's it. Is that the only possibility for the reaction? No, actually, you guys get two alkenes. It's only that this one is the major product, but you guys get two alkenes. What are the two alkenes? The two alkenes are formed here. When you guys form this carbocation, this tertiary carbocation, Remember that this one is a sigma bond. So this sigma bond can rotate, freely rotate. So you can produce that carbocation, or since this rotating, you can also produce this carbocation because it's this one is freely rotating. The methyl and the ethyl, right? They are rotating, freely rotation like this. So that means that the methyl can be on the right and the ethyl on the left because they're freely rotating. If you do the elimination here, you also do an elimination, but you get a different alkene. Okay, you see the alkene that you're forming? Do I need to do a Newman projection for this? No, no, you don't need to do a Newman projection. Just do it as because there's free rotation. This reaction is not stereo specific as E2. E2 is stereo specific because each hydrogen produces one particular type of alkene. Each hydrogen. Here in E1, no. One hydrogen, the same hydrogen, produces two types of alkene. So it's not specific at all. It can be selective, right? Because here definitely you can tell which one is a major product. Which one is a major product between these two? Just look at it and then just tell me what is the major product. You guys have 4 seconds. I'm gonna put it here. Correct. The major product is this one. Why is that? Steric hindrance. Always about alkenes is steric hindrance. My bulkiest group of this carbon is this methyl. The other one is hydrogen. That doesn't count. On this carbon, my bulkiest group is this group. So both bulkiest groups are trans. That's why it's major. Here, my bulkiest group here, my bulkiest group here. Both of them are cis. So that's why it's bad. Okay? So here's what we do for CCR, right? For an E1 reaction. This is E1 with carbocation, and then you have to do migration, CCR. What to do with alcohols, right? Alcohols are bad leaving groups. What should I do in the case of alcohols? Okay, in case of alcohols, something very special happens, which is the acid treatment. You have to use concentrated acid. What is that concentrated acid? Let's say I have this OH, and they treat it with concentrated acid, for example, sulfuric acid. Concentrated sulfuric acid. What happens here is that sulfuric acid is a source of hydrogens. Okay. It's a source of hydrogen. So the alcohol will get protonated. Of course, I get by sulfate, but sulfate is, but it's just a side product. Now here, oh, mistake there. It's only one lone pair of electrons, right? Okay. Because it's OH2 plus. So I attack, it got protonated. That's good. I mean, we learned that on chapter 7A. Now it's gonna do dissociation. Carbocation. And here is where technically you guys will do a substitution, but there is no nucleophile. I have no nucleophile. You say, like, oh, what if I have a more alcohol to do the nucleophile? Yes, but this one is not, because remember, the other alcohol is also protonated. All the alcohols are protonated. Once the alcohol is protonated, it's not nucleophilic anymore, right? So what should I do? Well, the same water that left is a weak base, right? Remember, guys? If it's a weak base, that means it's going to do an E1 reaction. E1 Zaitsev. What are my Zaitsev beta hydrogens? Here and here. This one is the Hofmann because it's the least substituted. Those two are the most substituted. Since the molecule is symmetrical, it doesn't matter which one you do. Okay, So let's just do the one on the bottom. So I have two hydrogens, and the water will attack, and here closes the alkene. Okay, that's the product. So this is called a dehydration of alcohols. Using concentrated base, concentrated acid. Anything that you guys see between brackets is always going to be concentrated acid. And then it goes through an E1 reaction. E1 reaction, if you have a tertiary alcohol and a secondary alcohol. If it's a primary alcohol, I think it goes through E2 reaction because it cannot form carbocations. Okay. Tertiary and secondary alcohols, they go through E1. If it's a primary alcohol, they will go through E2. Because if it's primary alcohol, it will generate a primary carbocation. And we know that primary carbocations are very unstable. So you won't be able to form it. Secondary carbocation, tertiary, yes, E1. But if you have a primary alcohol, it will have to be E2. How is that E2 in a primary alcohol? Okay, so let's say that you have this alcohol, right? And you also have sulfuric acid. This is a primary alcohol, right? We're all clear. This is primary alcohol. Alcohol attacks. Protonated, no proton transfer. OH2 plus. So technically, what we did here is leaving group, right? Dissociation. But if you do dissociation here, it will leave you with a primary carbocation, right? If you lose this, it will be a primary carbocation. You can't do that. So then what you guys have is, I mean, you have to add some water. Even though sulfuric acid is very concentrated, but remember that concentrated sulfuric acid is a mixture of SO3 plus water. So there's always water in the system. So you guys will have H2O. So H2O will have to, I mean, there's no other base. You say like, oh, but water is a weak base. And you said that weak bases do E1, no E2. Yes, but in this case, the sulfuric acid really wants to dehydrate the alcohol. That wants that water to be out. So it will pull it out. But it cannot pull it out without having an alkene. So it will help the hydrogen to be pulled off by the water, even though it's a weak base. Okay, so I know it doesn't look anticoplanar, but it should be an E2 reaction. Okay. Looks good. Okay, so I know it doesn't look anticoplanar, but it is anticoplanar. This one is an E2 reaction, only because it's a primary alcohol. Okay, so can I do CCR when I do this? Yes, absolutely, yes. So you can do CCR also with these reactions. So for example, if you have a cyclopentane and you have an alcohol here, right? Alcohol there, and then you have, let's say, two methyls, right? And then they tell me, okay, sulfuric acid concentrated. Okay, first step of this is protonation. And then I'm doing this mechanism, so you guys don't say like, oh, professor, your mechanisms are so easy and the exam are so difficult. No, I'm giving you a real case, something that like this you will see in the exam. Okay, so HHS4 mechanism, lone pairs attack out, OH2 plus protonated, the bisulfate, I have it somewhere, but doesn't really participate, it's a spectator. Okay, after this one is a secondary. It's a secondary alcohol, right? So definitely it will do an E1. Secondary alcohol, they can do E1. So I will do a carbocation there. Good. Right. So carbocation will give me CCR. Here's a secondary carbocation, primary carbon, tertiary carbon. Definitely I will do a CCR. Who is going to do CCR? The H. Migration. Carbocation. Okay, carbocation there. What is next? Beta hydrogen, right? Selection of the beta hydrogen. I have two beta hydrogens here and here. And they actually both give me Zaitsev, right? Because if I do it here, I will get a trisubstituted alkene. If I do it here, trisubstituted alkene. So in this case, you guys will actually get a mixture. You will do elimination in both positions. Producing what? Producing or why not here? Because this one has no beta hydrogen, right? Yeah. Those are my two products, two potential products for this elimination. Because there was a CCR, right? Yeah, that's also something I wanted to tell you guys, that sometimes you might say, oh, I don't have Zaitsev alkene. They both produce trisubstituted alkenes. So how do I decide if I do Zaitsev or Hofmann? If they both have the same branches, then in that case, there is no Zaitsev, there is no Hofmann. All those could be Zaitsev, or all of them will be Hofmann. So you will be producing multiple products. Okay, this is one case. For example, here in this carbocation, I had two options. I had two beta hydrogens, but both give me trisubstituted alkenes. So which one is Hofmann, which one is Zaitsev? None of them. Both of them are Hofmann, both of them are Zaitsev. I cannot distinguish. So it will be producing both. What if I use terburoxide, right? Let's say. What if I use terburoxide? Then there is no Hofmann, there is no Zaitsev. So both of them are Hofmann. If you're using ethoxide, both of them are Zaitsev. Okay? So when you guys cannot distinguish, right? We say like, oh, they're both the same. There is no Zaitsev, there is Hofmann. Then do Hofmann or do Zaitsev, regardless of what you are using, right? Okay, great. So this about the treatment with acid comes later, but I mean, actually, I just went ahead with the predicting products of steps. This is just mostly a review, right? How to predict the product. So here is a basically like a overview of all chapter 7. Here's the combination of SN1 and E2, right? Sorry, SN2 and E2. You only do it with these strong nucleophiles, which are very strong bases. So that's the only way you can compete with SN2 and E2. As I was telling you, like cyanide, for example, is only a good nucleophile, but it's a bad base. Okay? So this one will be the only nucleophiles that also serve as bases. If you are using a strong bases, sodium hydride, diisobutyl, I think it's diisobutyl, DBU. I mean, dibutylamine. This one is dibutylamine. Yeah, don't worry about these bases. If we haven't used any base, I mean, just discard them. No. But there's some alternative bases that we have in organic chemistry. Of course, they are not only using ethoxide and methoxide, right? They are more advanced bases that are more selective in some cases. E1, right? E1, these are the bases that you use for E1. Any alcohol, ROH, and water. Right? So that is based on the nucleophile. So E1, weak base, as E2 is a strong base. This chart is very important. I don't remember if I showed it to you, on chapter 7a, but this one really gives you a very good view of what happens in each situation. And you can see tertiary substrates are dominated by E2 reactions. The SN2 chances are very slim with a tertiary substrate. There's no way you can do SN2 with tertiary substrate. It's only either going to be E2, SN1, of course, SN1, and E1, very small. That's why SN1 is preferred over E1 with tertiary substrate. I mean, there's an even competition between SN1 and E1. For secondary substrate, yeah, that is dominated by A2 and SN2, right? You can see here how it's divided half and half. There is no case E weak base with nucleophile in this particular combination. And then primary, with primary, of course, SN2 dominates over E2. So you see the fight is mostly between E2 and SN2. SN1 and E1, they are very interesting to know the mechanism. This reaction, to be honest, has been even my professors were studying SN1, SN2. I learned it from them. They were telling me that also their professors were teaching them, teaching SN1, SN2. And they even the professor, my professors were telling that, oh, these reactions are old, very old. So you can imagine, like for you guys, this is an old of old of old of old. If we go by generations. So they have been well studied. In terms of teaching, it gives you really a lot of critical thinking. I love these reactions, E1, E1, E2, SN1, E2, SN1, SN2. I know it's very easy for me to say it from this side as a teacher, not as a student, but it really helps you for the later on, for all the reactions coming up soon, right? So let's take advantage of all this explanation. Hopefully, you guys are getting the idea. I'm crossing my fingers from the results, but I see every time I meet you in office hours or for questions. I'm very, very grateful that you guys are absorbing and catching these videos. Please keep going and watching these videos. They're available for you 365 days a year, 24 hours. So please just repeat it as many times as you want. If you want to share with somebody, please share the link. The videos are unlisted. That means that they cannot be found. If somebody, browses, no, they cannot find it. They have to be given the link. Without the link, they cannot watch my videos. All right. So let's continue. Here, this table, is good for discussion. But once again, you guys will never be placed in a situation where you guys have to judge if it's going to be SN2 or E2. Your reactions are either going to be only elimination or only substitution. But it's a good idea to have this comparison, right? Regioselectivity, stereoselectivity, just as a review, E2 reaction is Zaitsev, right? Favor over Hofmann, unless you use a hinder base, namely terburoxide, right? There are more, but terburoxide is the one that we prefer. Trans-substituted alkene is favored over cis-substituted, yes, because of less steric hindrance. Okay. In E2 reaction, you need the anti-periplanar. See, that one is what I was telling you. Sometimes they call it anti-coplanar, anti-periplanar. I think from what I'm reading right now, the process is called anti-periplanar elimination. And the configuration is called anti-coplanar. Maybe that's what I'm understanding right now. Okay, so the process of the elimination is called anti-periplanar. But the conformation, the configuration that has both groups opposite is called anti-coplanar. Okay, so I know it's just one prefix that is different, but the idea is the same. In E1 reaction, the Zaitsev product is always favored over the Hofmann. There is no Hofmann in E1 reaction. And of course, trans is more favorable over cis products if it happens, right? So remember, always think of bulkiness, steady hindrance when you guys are talking about alkenes. Right. So here, predicting the products. So here is I have a compound. I have to with sodium hydroxide. This one is a secondary substrate. Secondary substrate. It can do. If we talk about elimination, sodium hydroxide is going to be E2 reaction because it's a strong base. But if you put it in the context of substitution, it is also a good nucleophile. So it will be a competition between E2 and SN2. So let's take a look at the substrate. It is a secondary halide. Yeah, it's a good leaving group. Bromides are a relatively good leaving group. So SN2 and E2, yeah, will occur. But E2 will dominate. Why? Because secondary substrates are somewhat hindered and backside attack is more difficult. Yes, but I would also add that sodium hydroxide is a better base than nucleophile. So OH will prefer to do E2 rather than SN2. How do you know that, Professor Navarro? Because I've seen tons of reactions with sodium hydroxide and 65% of them give elimination and not substitution. It is like an internal survey. It's a survey of all my years of teaching. So that's my answer, really. That I've seen so many reactions and I normally see sodium hydroxide doing more elimination than substitution. Okay, so consider the review and stereochemical requirements on E2 product. Okay, so I have different beta hydrogens. Basically, the same analysis we've been doing in all my examples. Here you have your alpha carbon right here, and you guys have your beta position, beta, beta, and then you have to decide which of these beta hydrogen will be eliminated. So you eliminate HA, you will get this alkene. If you get HB, you will get this alkene, right? Cis and trans. One of them is going to be cis, the other one is going to be trans. Or you know that the cis is favored, right? It's favored over trans. What if I eliminate on any of the HCs? Okay, you get a Hofmann elimination, right? Which is the least attitude. You don't want that. Professor Navarro, why do they label HAHB and at the bottom they label C, all of them? Why didn't they label HCDE? Oh, because in CH3s, they're all different. Sorry, they're all equivalent. CH3s, because there is free rotation, they all have, I mean, they're all the same. And also because they produce the same alkene, right? It's a terminal alkene. Terminal alkenes, they don't really have any restriction. But if you have a CH2, yeah, the CH2 is a problem. One is a cis, one is a trans. If you have one H, yeah, that's an issue because then you have to come up with a Newman projection. The major product is this one, right? Because it's trans. It's a Zaitsev because you were using sodium hydroxide, which is an E2 Zaitsev base. And then in the Zaitsev base, you prefer the trans product over the cis product. In the case for alcohols, right? If you want, other substrates, you can make alcohols into good living groups using these groups: tosylates, methylates, and triflates. The one that we've been using is tosylate, right? OTS. OTS is a good living group, and we can do that by a reaction between the alcohol and tosyl chloride in pyridine. Okay, I was just reading an article, very interesting. I mean, you guys want to research on that this particular smell of bacon is pyridine. Pyridine is one of the molecules responsible for bacon. So watch out, male students, that pyridine is sterilizes men. So high exposure or constant exposure of pyridine, it really does something to the cells that it produces less male cells, right? Or decreases the hormone level, something like that. But pyridine, that's something. So I was reading about that just now. So bacon has pyridine, and that smell of bacon that you might feel like smells good, so that has pyridine, so watch out for it. Okay, so we use tosylate, tosyl chloride pyridine with the alcohol, it will give you the product. This is the reaction I was going over with you guys. Is the concentrated sulfuric acid in an alcohol. In this case, they have tertiary. Tertiary, of course, it will do elimination. Again, strong acidic conditions are product condition. We favor E1 for E secondary and tertiary substrate. For primary substrate, it should be E2. Okay, so the secondary and tertiary substrate, you can do an E1 reaction. The mechanism is here, very similar to what I show you, right? Alcohol gets protonated. The first step, water leaves forming the carbocation. Here you can have a potential CCR. In this case, that doesn't happen. And then water as a weak base will remove that beta hydrogen, forming the alkene as a product. Okay, it's an E1 mechanism. This one, so we also went over this in the previous chapter 7a. That's an overview of all the reactions we've been doing in this particular chapter. This one is concentrated on 7b. Right? So you have a substrate. In this case, they have a tertiary substrate with sodium hydroxide, right? You can form the alkene, Zaitsev product. If you want a Hofmann product, you have to use the butoxide, which is a bulky base. You can also, from alcohol, go to alkene using a concentrated sulfuric acid, right? From this last reaction we learned. If you want to produce an alcohol from an alkyl halide, you can use water. If you want to go from alcohol to alkyl halide, you can use HBr. You can also do HI. If you want an iodide, you can use HCl. If you want a chloride, but you cannot use HF. Don't use HF because fluorides are complicated. If you want an alcohol to become a good living group, then you will add tosyl chloride in pyridine to get it a tosylate. And tosylate are also good living groups, which you can do sodium hydroxide and butoxide if you want to do Zaitsev and Hofmann. Very, very instructive, very detailed chart that I definitely recommend you. Can we use these charts or tables for our exams? No, unfortunately, no, guys. Okay, I'm sorry, but that's the way how we all have to learn. It's a process. You guys have to have the tools and then apply them in situ during the exam. In situ. Right? Okay, synthesis strategies. Yeah, that's something that I was telling you about, right? The synthetic analysis. Let me think of one more. So that's how we're going to be closing this particular lecture. Is the synthetic analysis, right? So we're thinking about how to make something, we first think about what the finished product will look like, right? So if my product is an alkene, so definitely I know that I have to make it from either E2 and E1. But from what we just learned, E2 is the way to go. E1, there are very slim chances. There are more in E2 reactions. So I will have to think of E2 instead, right? So let me see, how can I actually, maybe I'm just thinking of something. Okay. What base is needed? This is actually a very good problem. Okay, this one. What do I need? What reagent do I need to go from here to here? Okay, I'll just give you a few seconds. Okay, so OH, right? It's a bad living group. I know it's a bad living group, so I need to make it into a good living group. There are different ways how to make it into a good living group. But the thing is that if I make it a good living group, the alkenes should be, the possible alkenes should either be here or here. Right? Those are technically my possible alkenes. Is the product showing that? No, right? The product actually has the alkene here. What happened? How can I have the alkene in a different position? Which of the two reactions allows me to move things around? The only one that allows me to move things around is E1. Why? Because it produces carbocations. If it produces carbocations, it can potentially produce CCR. Can I do E2? No, because E2 only does with neighbors. You cannot move things around. Okay, that's something good to know. Then what should I do? Okay, so you want to do something, I mean, you actually can do the best way would be with a sulfuric acid concentrated. Because you sulfuric acid concentrated, it will go through E1. And E1 can do rearrangement. Okay, so that's the only step. That's the only thing. That's the only way how you can go from here to here. There's a longer way, but it involves substitution. I mean, now the shortest and the most effective way would be with sulfuric acid. Let me show you the mechanism. And then with that, I'm closing this particular chapter. If I'm putting a lot of mechanism examples, definitely expect mechanisms on the exam. Okay. Sulfuric, I mean, the OH attacks gets protonated. Secondary substrate can do E1. Dissociates, it forms a carbocation, which is secondary. secondary carbocation. The secondary carbocation can do CCR, secondary, tertiary, primary. The hydrogen migrates. Now carbocation there. Okay, now where are my beta hydrogens? My beta hydrogens are here, here, and here. I have 3 beta hydrogens. Which one is the one that's going to be the best? Well, this one, if I create this alkene, it will be disubstituted. If I make it here, it will be trisubstituted. If I make it here, it will be tetrasubstituted. Of course, this one will be my tetrasubstituted. Okay, so I'm going to remove this hydrogen. So water will attack here, and this one comes. Now, actually, it's a good example. It's a coincidence that it came out this. Here, it forms 4, right? 4 branches, 2 branches, 3 branches. Then how can we label it? 4 branches, right? Tetrasubstituted would be Zaitsev. Disubstituted would be the Hofmann. What about the trisubstituted? Is the trisubstituted going to be Hofmann, Zaitsev? Actually, no. It will be less. I mean, it will be on the scale of on the Zaitsev side, but it will never be the major product here. I cannot get a major product here, never. Even if I use Zaitsev or Hofmann elimination. Why? Because it's in the middle. It's not the most substituted, it's not the least substituted. It's in the middle. So how can I favor it? No, then you cannot favor it. You will have to do an E2 and then maybe do a migration, and then actually that's another good problem question. How to make an intermediate, right, branching into a major product. That would be a challenge. Yeah, I'm thinking right now of a problem like that. Right. So that's the idea, right? So if you guys have an alkene that is my Hofmann, sorry, that's my Zaitsev. This one is my Hofmann. I mean, what about this one? Is this Hofmann, this Zaitsev? No, none of them. This one is your Zaitsev, this one is your Hofmann. That one will be nothing, really. You cannot get it as a major product, never, right? So going back to the problem, this one will be my alkene. And this is exactly the same as the alkene that I was expecting, right? To synthesize. That contains ECR. I had to do E1 reaction. I cannot do E2 reaction. And one example that you have to do synthesis, right? Let me see synthesis. Okay, so let's say that you guys have an alcohol. Um, yeah, not too difficult. I mean, we don't have too many reactions. After chapter 8, I'll definitely come with more surprises. Okay, so this one is an alkene. The only way I can make alkenes is E2 reaction, also E1. But in this particular, I know that always pay attention more to E2. So here is my, if I look at the structures, they both have about the same skeleton. Here is the alkene, right? The alkene to be, right? And then that has the leaving group. Okay, so if it has the leaving group, no problem. Why? Because I know that I'm doing an E2. If the alkene is not on the leaving group, then that means it's an E1 because I have to do a CCR. So here is on the leaving group is on the alkene. So good. So I know it's E2. Now E2, I know that I can do Zaitsev or I can do Hofmann. Which one is it? Okay, leaving group, here I have 3 potential alkenes. This one is the disubstituted. This one is the trisubstituted. Definitely it's a Hofmann. So can I do Hofmann directly here? No, because this is a bad leaving group. Can I do acid treatment? No, I cannot do acid treatment. You only do acid treatment when you use sulfuric acid concentrated to produce the alkene right away. But to make it a good leaving group, no, you can't. So you guys have to do first a tosylation, tosyl chloride with pyridine. That tosyl chloride with pyridine will give you the OTS. And then here I can do terburoxide. Potassium terburoxide in terburanol. don't worry about these details. I mean, you can just write simply terburoxide, but don't write potassium, right? Because potassium doesn't tell me anything. You guys have to just simply write terburoxide. That's all you need. And then that one just give you this product, right? Whenever you guys do synthesis, you don't have to write the mechanism. It's only the steps. When you ask the product of a reaction, also you don't have to write the mechanism. Only when they clearly tell you, please do write the mechanism for this reaction or do the Avro formalism for this reaction. Yes, in that case, please do it. All right, so that's all I have for now, guys. Hopefully, I mean, this lecture has helps for this chapter 7B. I'll be coming up. I mean, I will see you soon for chapter 8.